So there's a lot of topics. 1Password, it's a huge system. It's really complicated in some ways, and it's really kind of elegant in other ways. We'll talk about a few things in particular, how you're logging in, how vaults are shared, how you handle multiple accounts, things like that. The talk is fairly high level, but I do have some deep technical stuff thrown up there, but I'm not expecting people to really grok all the really crazy technical stuff just from listening to a slide for 30 seconds at a time. I do have an extensive series of blog posts that kind of goes into really deep technical details, and the idea there is I want to have enough information there that if somebody really wanted to go and do this themselves, that they could do it. One thing I'm not going to do is compare this to other tools. There's lots of password managers out there. Some of them are really good. I've been using 1Password for close to 10 years. I've always liked it. It's what I use. I'm not going to spend a whole lot of time to do a formal review of other systems. Like I said, I'm here to figure out how the little crazy cryptos work. I'm not really here to compare one tool to another. If you really like another system, like LastPass or KeyPass, or I'm not even sure what else is out there, maybe this inspires you to do the same thing and do a talk next year about how that system works. That'd be great to see. So we'll talk a little bit about some words and terms. Some of these are kind of specific to 1Password or how 1Password uses them. You've got your account, which is a group of password vaults, or just a group of places where you store passwords. So you might have a work account, you might have a home account, you might have a volunteer job that you do stuff with account. Vaults are where you keep your passwords, and they don't have to be passwords in 1Password. They can be notes, URLs, serial numbers, one-time password, token, things like that. But they're all just items. They're stored in the vault. The two things you'll hear a lot in here are the master password. That's what you type in when you unlock the client, and a secret key. Originally, they called this account key when they rolled out their cloud service, and it's a long string that you get, and you'll see a little bit more about that as we move on. And yes, I didn't say this up front, but we're really focusing on the cloud service, partially because that's kind of what they're moving towards in general. It's also the most useful in a family or a team or a work context. It's also in a way the scariest. 20 years ago, if you had said, we're going to put all of our passwords on somebody else's server in the cloud, you'd say, you're crazy. But that's exactly what we're doing with this, and that's why a lot of people are scared is, well, shit, this is on somebody else's computer. Can I trust it? And again, that's why we're looking into it like this. And they make it all work with cryptography. Like I said, I kind of like crypto puzzles. I'm a cryptography dilettante. So I kind of understand enough to be dangerous, and I don't expect people here to be experts in any of these things, because I'm certainly not. Some quick terms that we'll just be tossing around a lot. AES, the Advanced Encryption Standard, is a symmetric key encryption. That means that you use the same key to encrypt it and decrypt it. Compared with public and private keys, in this case RSA, is a pair of keys, and you can encrypt data with one key and decrypt it with the other. And that becomes very, very useful for parts of the system here. Their hash functions, I'll go a little bit more into how hash functions work. And I'll talk a lot about key derivation functions as well. All of these things are used all throughout 1Password. If you already understand what these are, terrific. If not, despite what I just said about avoiding black boxes and wanting to understand how all the black boxes work, treat these as black boxes and just assume that they work. Right now, it's just the larger picture that matters. If you want to go deeper into crypto, absolutely, it's a fun place. So, we got a lot of content. It's actually a really simple system to understand. And yes, it really does need to be that complicated. So we're not going to build everything from first principles here, because that would be insane. But let's start building a really simple password manager together. So the simplest thing you can do is just have a list. So you've got a Notes app on your iPhone. You put all your passwords in a list called Passwords. Hopefully your phone is at least locked. Maybe it's not. So that's a great way to do it, except that if somebody opens your phone, they open the app, now they've got your passwords. All right, so let's not use Notes app. Let's use an app that's dedicated to passwords, and we'll put a little passcode on the front of it. The data is still not encrypted. The passcode is just simply a number that's stored somewhere on the disk. So if a hacker gets hold of your device, they find where the passcode is, they can unlock the app. They find where the data is, they don't even care about the passcode, they can get your data. All right, so now let's encrypt the data. So how do we encrypt it? Well, you've already got a passcode. Let's use that as the crypto key. So you type in the password, or actually here in my example, I'm not using this key here. We've got a key that's stored on the disk. You type in your password, it verifies the password, it gets the key, it decrypts the data. So now the hacker has to get at the encrypted data And then if they can extract the key or your password, again, they've got everything. So far, none of these are really very good. So now, let's actually encrypt the key. And we won't actually store the password on the disk. Now we're starting to get where it's reasonably good, because a hacker could steal the encrypted data, but they can't do anything with it without the key. They can steal the key, but in this case, in all my diagrams, double box means it's encrypted. Mostly, I'm probably messed up on a couple of slides, but in general, the double box will mean it's encrypted. So in this case, the key is encrypted. So yeah, somebody hacks your phone, they get the key, they get the data, but they can't do anything with it because they're both encrypted. So what you need to have is the password. So now the password isn't stored on the system. It's relying on the user to type it in. The password decrypts the key decrypts the data, and now you got it. The problem with this approach is that passwords make really lousy encryption keys. You brute force passwords by picking a password, trying to see if it works. If it doesn't work, you pick another password, you try and see if that works, you keep going. A way that we measure how safe a password is through entropy. In this case, it's, for example, the word password, which is just 8 lowercase letters. If you assume that they're only coming from the alphabet of lowercase letters, it works out to about 38 bits of entropy. Not a whole lot. A good encryption key should really be about 128 to 256 bits of entropy. So you can see the word password, all lowercase letters, is just no good. So that's where we have ways to try and turn a password into a strong key. You can do that with lots of things. I mentioned hash functions earlier. Again, we're going to see these all throughout. A hash function is basically a function that takes an arbitrary input and spits out consistently a fixed string of bits. What's important is that the output is completely unlike the input. It's indistinguishable from randomness. It's got to be consistent, so the same input should always produce the same output. And it needs to be irreversible, so you can't take a hash and go backwards. It's not encryption, it's a one-way function. And then also they're divergent, in that hashes of very similar text can be totally different. And I'm trying to illustrate that here. We have 3 different words. We're hashing password 0, password 1, and just password. And you can see that in all but 2 nibbles, so all but 8 bits, they're completely different. And the text is very close, but the hashes are totally unlike each other. So again, hashes are consistent, that's great. But the problem with that is now 2 users that have the same password will have the same key. So now if you go back to the scenario where somebody steals the phone, now they can possibly just go through a whole bunch of simple tasks. They might have a rainbow attack or some kind of another attack where they know what the ciphertext looks like. They just say, oh, this ciphertext looks like this, that means the password is this. So what they do now, what we can do is we can add a salt. And what that is a random string that you get added to the password that makes it more unique. It makes it a unique string. It's not a secret. It can't be a secret because the system needs to know what that salt is in order to eventually apply the salt to what the user types into the keyboard. So now what we've got is you have a salt that's stored on the disk. You have a password. You type in the password. It takes the password and the salt together, runs them through some kind of a thing, produces a key, which then decrypts the data key, which then decrypts the data. Starting to get a little bit more complicated, but it's a lot more secure than what we had on the last diagram. So far, we're just talking about clients, your phone, your laptop. We've also, in this case, got a very strong cloud component. What about stuff on the server? Obviously, you've still got to worry about things like password cracking, even against the server. If somebody gets hold of the password list, they crack the passwords, now they can decrypt your vaults, now boom, they've got all your bank accounts. One obvious thing is, okay, let's just make it two-factor. Use a two-factor authentication. That's great for authenticating. It doesn't really work for crypto because the key changes every 30 seconds. So you're never going to be able to decrypt your data if the key is constantly changing. So what AgileBits, the people who make 1Password, did is they added a concept called the secret key. In this case, now an attacker wants to attack things needs 2 secrets. They need the master key, password, you type in, and they need the secret key. The secret key is that long, crazy-looking string there. And there's actually, there's multiple components to that have specific meanings. We'll get to those in a minute. But this secret key itself is about 129 bits of entropy. So this actually is a pretty strong key just by itself. So there's a lot of ways that you can then mix that in with the password. You could, so now you've got a password, and then maybe you hash a password to get some kind of a key. Now you got the secret key to make it a little bit more complicated. How do you pull those together? One thing you can do is you can just mathematically add those strings, express them as numbers, add them together. The problem there is that you might end up with a number that's bigger than you need. So in this case, because of addition, you get a carry bit, and you have that extra digit on the left. If you're only looking for so many digits, and now you've got an extra one, you can throw that away, but that might have cryptographically pertinent implications. There are times when you do simple things like that and throw extra data away, and actually makes things significantly weaker because of some foible to how the algorithm works. You can also just glom them together one right after the other, super fast, but now you've definitely got a big key. You can also use a logical exclusive OR operation, which just takes them kind of together and does some sort of bit level matching between them, and you end up with a string that's the same length. So that's what you do here. That's what's done in a lot of cryptography is the XORs. So now we have a secret key. There's that long string. We have the salt, and we have the password. Put all those things together. It does some magic on it. Matches it up in a galvanized tub. You end up with a key that you can then decrypt the data key, but now you can decrypt your password. This is great. We took a short password, and now we have a 256-bit key. That's terrific. But you can still guess the password, because everything that I said has turned a password that's short into a key, which is big, but it does it instantaneously. It's just a couple of quick hash operations and some exclusive ORs and stuff. But you can still brute force it. You've got the password, salt. if you have the password and you have the salt, but you don't have the secret key, you can derive the first part, and then you got to brute force the secret key. Okay, that's going to be tough because the secret key, I said, was 128 bits. That's huge. You can't brute force that. But if you haven't protected the secret, and you've got that, you've got your salt, but you still need the user's password, now you just brute force the password. Now we're back to the normal problems of pick a strong password. And that won't take much time at all because, again, the key derivation that they use here is super, super fast. So they slow it down by doing it 100,000 times. They still recommend a strong password. And actually they have, their current recommendation is to use a 4-word passphrase. But just to make sure that that's really strong enough, they actually started a competition in May where they had, they published a list of 18,000 individual words, just a dictionary of words. And they said, okay, we've got, I think, 5 different hashes that we generated by selecting 3 words from this list. Their recommendation is 4. They said, we're going to make these passwords only 3 words, and we want to see if people can break it, because we want to have an idea for whether the 4-word is really a sufficient recommendation or not. If they stuck with 4 words, and it is sufficient, then the password challenge would never be broken. So that's kind of why they weakened it a little bit. This started in May, and as of October 24th, somebody finally cracked one, and then literally just 2 days ago on Wednesday, I think the same team announced that they had cracked the second one. They haven't announced quite how they did it, what kind of rig they had, stuff like that, but it ended up taking a lot longer than the 1Password company thought it was going to take. They actually ended up giving out some hints. They doubled the prize payout twice, and then they started giving little hints as to what the passwords were. They gave little hashing hints to try and help people speed it up a little bit. And so even with that, it still took them close to 6 months to crack the first one. So if you figure that that's 6 months and add a 4th word, could multiply it by 18,000 times, 4 words is probably pretty strong. All right, so let's pull all this together. We have a password, we have a salt, we have a secret key. You have an email. We didn't talk about that, but obviously you've got a cloud-based account. You've got an email that's associated with it. Mix them all together, and that creates a final key. They call this the 2-secret key derivation process because there's 2 secrets, the master password and the secret key. And so this is technically what it looks like, and this is where it starts to get a little bit more deep. You have the password salt, which is going to be unique to your account, or probably unique. I don't know if they've actually enforced that. But it's a random number that's just assigned to your account when you create it. They have a string, that PBES, 2G, whatever, that helps to describe the algorithm, and then your email address. They jam all those together through an HKDF function, which is a special key derivation function. The result of that gets fed into the key derivation function, which then gets joined up with the results of the secret key, and you end up with the final master unlock key. The HKDF step, it's the HMAC key derivation function. There's a specific RFC for it. It takes 3 parameters, and then this describes the different parts of the parameters. So for the first part, you saw here the email address, the salt, and that algorithm name get kind of put together. The key is the salt is the email, the info is that extra bit there at the end. And then for the secret key, is actually split into 3 components. The A3 is the version, which I guess matches the version of their system, their algorithm. The account ID is the next bit, and that's the only part that Agile will retain. So if you call up and say, I'm having a problem with my account, they can say, oh, is it the account that starts with ASWWIB? You say, yes, it is. You'll know you're talking about the right account. If you don't have it, then you know you're not talking to the right account. And then the last, 5 groupings there is the actual secret. So now we've got something that looks a little bit more like this. Your password, all those extra things, all thrown into the 2-secret key derivation, decrypts the local key, decrypts the data. Well, again, we've got math, lots of crypto. There's a really cool system called the Secure Remote Password Protocol, which implemented properly is reasonably strong. There's also some bugs that people have discovered over the years, and you have to be careful when you implement it. This is why I don't write crypto. I find other people have written crypto properly and use their tools instead. Basically, the way this works is there's 5 specialized functions, 5 specialized math equations. You take your password, call it X, and from X, you pass it through a single function, you get a verifier. The verifier is what you send to the server. So you never even send your password to the server when you create the account, you just send the verifier. The verifier is kind of like a hash. It's easy to compute, but it's very difficult to go from the verifier backwards to the password. So the client, only the client ever sees your password. And so the way it works is you take your password and some random data, run some function on it. The server takes the verifier they got, some other random data, runs a function on it. They exchange the random data with each other, so each one knows the randomness that the other one picked. And then they do some more functions, and then the result, because of the math, should be that they both come up with the same number. If you both came up with the same number, then the client has proven that their password matches what was used to generate the verifier, and you're in. If you have the verifier, but like I said, you can't reverse it to a password, and in this case, you can't calculate the second part because you need the password to get the first part, and like I said, it's the math is all there. And here's the math if you want it. You can look it up in the slide later, or the Wikipedia article describes it pretty well. It's neat if you just like math. But again, we need to have a strong password. So we've got the master password, we got the secret key. Together, those make an incredibly strong password. We could just use that. I mean, that's a 256-bit password. That's equivalent to 39 characters of the full 96-character principal ASCII. If you could reliably create passwords that are utilize that full character space, that's a pretty good password. So we've got that. We could just reuse that, but we shouldn't, because you shouldn't reuse passwords. Even though it would be reasonably safe, you still don't want to do that, because then if something gets captured in the wrong place, now they've got access to that. You just don't want to do that. So what they do is they take the same process, the 2-secret key derivation. They change the salt, they change a couple of other parameters, and use that to generate the verifier, or in this case, or not the verifier. This is the password. So this is sort of the replacement for your password that then gets turned into a verifier and sent up. But it's exactly the same as what they use for the master key, only they have a different salt, and they change the algorithm name to SRPG496. So these are the 2-secret key derivation again. Everything takes the master password, your email address, it's got stored in the account. When you create it, there's randomly generated salts, both for the password and for the SRP. And then you've got different names for the algorithms. Those are used to generate the final keys that you use for local vaults or for the server. So on the server, there's a lot of features that are only available through the server. You can do most everything you want through the client, but there are a lot of account level features that are on the server. And again, I'm not really going into account detail or application level details, but figured it's worth mentioning. On there, you can do things like you can manage who has access to what vaults. You can change your account password. There's billing things, because obviously it's a cloud service. You have to pay for it somehow. But the SRP can't be used to decrypt the vault. That's very important. The vault data that you have is encrypted with the first half of the whole system. You can't, even if you get the SRP, even if you're able to regenerate that or steal that somehow, you still can't decrypt their data, which means that Agile bits can't decrypt your data. They have no way of getting into it at all unless they have your password, which hopefully they don't. All right. So it's great to have just a password list, but if you're working in an organization, working in a team, you've all got to share access to the different servers. You might want to be able to share passwords with one another. How do we do that? You could, create different lists. Everybody's got their own list. You log into different accounts. You can pull down those. Okay, that works. We could take a step backwards and think about how we might have done this, in Victorian era. So imagine a wall full of small drawers. All right, you've got a drawer which has got little index cards in it, and each index card has a password. You get a new password, you write it down there, you put it in the right space so you can find it easily. You close the drawer, you lock the drawer. Now you're the only one with a key. Your passwords are safe. Nobody else can get into that drawer. We'll forget about the lockpick village upstairs. So now, if you've got passwords you want to share with the team, you create a new drawer. And you create 3 keys, one for you and one for your 2 team members, and you go and you give them the keys. All right, so far so good. What happens if somebody on your team isn't around when you generate the key? You can't just, when you create the new drawer, you can't just go and leave the key sitting on top of their desk. So what you do is you give everybody one of these little toy bags that has a coin slot on the top and a combination lock in front. You go over to your team member's desk and you drop the key in the box. Now you've given them access to this drawer, but you haven't had any way you haven't had to do anything other than just drop it through the desk, through the slot. Then your coworkers can unlock the combination, get out the key, turn the key, open the drawer, and now they get access to the passwords. And let's say also you want to make sure you don't forget the combination. You write the combination down on a piece of paper, seal that in an envelope, stick that in the desk, and lock the desk. Now you've got a backup as well. So create a new vault. Again, you make a copy, go around, slip in all the keys. So this is kind of what it looks like. You've got the combination written down, stored in an envelope, locked in your desk. It unlocks the key box. The key box contains the keys, which open up the drawers, which has the passwords. That's exactly how 1Password vaults work. In this case, the master password key, which is the master unlock key you get when you type in your thing, go through the whole 2-secret key derivation. That is equivalent to unlocking your desk, which gives you access to the vault keys, or key set keys, which is a combination. You unlock the key box, now you get the thing. So it's, in this case, you've decrypted an AES key, which decrypts a private key, which decrypts individual vault keys, which are equivalent to what you did for the drawers, and then you get the items. So it kind of looks like this ultimately. It's starting to get a little bit weird, but hopefully the analogy helps to make it a little bit more helpful. So again, I mentioned with the private and public key, the way the private public keys work is, if I encrypt something with somebody's public key, only the person who holds the private key can then decrypt it. So the public key is equivalent to the key slot. Or coin slot. You drop the key slot, coin slot. It's just like encrypting something with a public key. You can give it to them, but you can't get it out because you don't know the combination. So that's how this is working with this. You add somebody to a new vault. You take the key for the vault, encrypt it with that user's public key, and then send them that encrypted part. Now they can decrypt that using their private key and get access to it. What happens if you forget your password? Where's the one here? You might have one for David, one for Dom. Everyone's got their own ones. You might have some for teams. There'll be another one just for admins that only admins have access to. It's not normally downloaded to their client, but they can get access to the contents of that through the server as they need to. So basically, you need to reset your account. You go through the process. Eventually, the admin gets an email, says, "Hey, are they going through with this?" And you say, "Yes, do this." And then all of a sudden, the admin now has access to your key that they can then decrypt and then re-encrypt with your new public key for the new account that you just set up. So basically, the recovery isn't so much recovering an old account, it's nuking everything and starting from scratch. But because of the way the shared vaults work, they can get access to your data again and send it back to you. So not nuking the data, they're nuking all the keys. No, I'm moving faster than I thought. So how does this deal with multiple accounts? It's 1Password, so you have 1Password. And this is one of those things that has always worked for me, and I didn't really stop to think about it until I started down this path a few months ago, and yeah, how the hell does this do this? So what happens is you have the primary account, on your client. So the first one you kind of set up when you set up the 1Password client becomes the primary. As soon as you unlock that, that can then unlock the other accounts. So on the Mac, what this does is it works with the master unlock key. Again, you type in your password, you have the secret key. It runs through the 2 secret key derivation process. You get the muck. The muck decrypts your primary account vault, and then that goes ahead and decrypts some additional data that's stored for all the secondary accounts. So in another accounts table, there's a line for this account, a line for that account, a line for the other account. All those are encrypted with the muck for the primary. Once you decrypt that, you get the master key for those second accounts and the SRP key. So now those second accounts can reach out to the server, pull down updated versions of the vault. They've got the master key, they can unlock the key sets, get to the data. On Windows, it's a little bit different. On Windows, they don't store the secret key locally on the system like they do on the Mac. Instead, what they have is an encrypted master key structure in their database that then goes on and decrypts those individual account things. So Windows has this extra step at the beginning, where you type in your password, it pulls a salt and a list count of iterations, runs through the password-based key derivation function to create another key that decrypts the master key. That decrypts a piece of data that includes the user's actual plaintext secret key and plaintext password. Those are then fed into the 2 secret key derivation process and creates a master unlock key, and from there it goes on like the others. Some low-level technical detail if you're interested. The master key structure tells you how many iterations there are, and then how long your salt is, provides an actual salt. So this kind of helps you to, this is what derives the key that then decrypts the next part, which is an OP data vault structure, which is just a format for storing encrypted data that 1Password uses throughout. Not super important to know that right now, but it's there if you want it. So basically, you type in your password. It does, again, the password-based key derivation function, only in this case it's using a different hash function associated with it, the SHA-512 hash. And then the iteration count varies with each computer. So if you set up your account and you unlock it, it takes a couple seconds, great. If you move that account, that whole installation to a different computer, upgrade your computer, whatever, you move your data over, and you unlock it, it takes a half second, and oh, that's too fast. Half second is too fast. We're going to change this. It will re-encrypt the master key with a higher iteration count such that it always takes about a second to unlock. They want to make sure that that's not something people can brute force. So you type in your master password, it pulls the information from the EMK structure, derives another key, that then decrypts the payload, which contains a master key and a signature key. The signature helps to verify that the master key hasn't been tampered with, and then that goes on, decrypts the account data and the accounts table, and then goes on to get the actual data. So now we've got multiple accounts. This is kind of beautiful. It's not really readable on this screen though. So on the Windows, you have your unlock password, derives the master key, which then decrypts in a account information blob, which contains the actual password and secret key for each account. That uses the 2 secret key process, decrypts the key set, which then goes down and decrypts all the data in the vaults. And then that can also decrypt the next account, which is the same thing, and so on. On the Mac, you go straight to the 2 secret process. It then decrypts the first key set, which can then decrypt the second account data, which then decrypts the second key set, et cetera, et cetera. So all that just brings us back to where we started. Everything that's on here we've now talked about. That's a simpler view there. Which again just kind of puts it all together in one place. The Windows password, which unlocks certain data which contains information that is just simply provided by the user on the Mac, which then derives master keys, which unlocks the primary account, which then unlocks the key set for the next accounts, and so on. Moving away from the microphone, a cough doesn't help when the microphone is clipped to your lapel. So where's everything kept? This is, again, I kind of went down this path to sort of assess risk. The question we were trying to answer is, so what happens if somebody gets your master password? What can they get? And the answer to that was, I think everything, but I'm not sure. And so that's when I kind of started going down and digging. And so that's where I found out where everything was stored. On the Mac, all your data is stored in SQLite database, stored in your library. The secret key is actually stored in the system keychain. And then the master password obviously is in your memory, and you type that in. On Windows, the vaults are stored. So I was supposed to go and find out exactly what it is. I haven't really used Windows extensively for years and years, so I'm not sure I could even answer that question clearly, but there's sort of the equivalent to library on Windows boxes where you've got sort of all your application data that's stored.
Program data.
It's down in there. And there it's again, a SQLite password database. It's a little bit different. The secret key is not stored anywhere else. It's stored encrypted in the vault along with the master password. You have a different unlock password that probably will, in practice, be the same as the master password. But you type in the password, it then decrypts those other things to the vault and goes on from there. And then web browsers is a little bit different. Web browsers don't store the data locally. They don't store the vaults locally. They'll, once you've authenticated the system, it's sent the SRP off to the server, comes back, says, okay, you've got all these vaults. Says, okay, tell me what's in this vault. Says, okay, here's the vault. You decrypt it locally. So all the encryption, decryption is happening in the browser. But one important thing that I did figure out is that when you log in using the browser, there's a little button, you remember this computer sort of thing, and usually that's just cookies and whatnot. In this case, when you select that, it also stores your secret key in the browser's local data storage. So that's great because you don't have to find a piece of paper that's got a secret key and type in that long A3-XYZP whatever sort of string. But it's bad in that if anybody can access your browser cache, they can extract it. It's stored in there encrypted, but because this is before you've done any password stuff, there's no, it's a fixed key that's dedicated to the application. The key is actually the SHA-256 hash of the string. Obfuscation isn't encryption, but it doesn't hurt. So it's there.
I'm sorry, is there any timeout? Because I remember once you enter the key the first time, it works, but then after a while, you kind of forget.
Is there a timeout for the browser? Because sometimes it seems like it's breaking the secret key. I don't know if there is or not. It might be that maybe you just didn't click the remember this computer, or maybe it does time out after a certain amount of time. I'm not sure. I really don't use the browser interface except to do the account level things, like managing vaults and stuff like that. But that is something that we were concerned about because, again, the question was that we had presented to me was, what happens if a machine is popped and they can keylog your master password? Well, if they're on the box and they've got the password, then they can eventually get access to the secret key and they can eventually get access to everything. So the secret there is just to make sure your box doesn't get popped. So to wrap up some of these details here, we've talked about the secret key. The main thing for that is it really gives the resilience to password breaches of the server. The master password is what you use to unlock everything. You don't actually send the password over the wire to the server when you're unlocking at the cloud level. It's doing secure remote password. And even the password, quote unquote, that you use to authenticate to the server, even though you're not sending it, isn't your actual password you type in. It's, again, a derived password of 256-bit strength. There's shared vaults that you can then share with other people. There's a recovery function that your team organizers, admins can use to help you recover passwords that have been lost, or your account access, which then you can get back to your vaults. If you delete something from a vault, I don't think there's anything you can do about it. There's a whole lot of other features in 1Password that I didn't touch on. There's Watchtower, which is a nice thing that it actually has a server interface that it can talk to and say, hey, tell me what the latest breaches are. And so you can say, oh, you've got an account at such and such. Did you know they were breached on such and such a day? And it looks like your password was last changed before that day, so this password may be at risk. There's another variant of that where the service, it's a third-party service, not one that they run. And I apologize for not remembering it. It's an outgrowth of Have I Been Pwned, but I don't remember the name of the secondary service that does this. But they actually take all the pwned passwords that are found, and they build their own database, and you can hash your password locally and then take the first, I think, 5 characters of the hash and say, hey, send me any hashes that match this. And they'll send you back, it's about 100 hashes or so typically. And if any of those match the one you've got, then you know that they've got the password you just found. So that's a way to say, hey, this password you've got for X account, that service hasn't been breached, but what you think is a strong password has been seen on some other password lists, which means that it's now on dictionaries that hackers will use, so now you might want to change that password too. So Watchtower is a nice feature. Travel mode, actually, you go into the web client, you can say, I'm traveling, and it basically deletes your vaults from your devices. They all still exist in the cloud, but they're gone from your devices. So if you're going through customs at a hostile country, then they can look at your phone and there's no passwords on your phone. It's just not there. And then as soon as you're done, you click travel modes off, the vaults come back. And it's fast. I mean, I literally tried that, and I went back over here, typed ls, and the passwords were gone. The database was gone. There's some two-factor support, both for authenticating to 1Password, that you can force it to ask for a two-factor token. You can make them authenticate with a two-factor every time, or once a week, or something like that. It also supports time-based one-time passwords inside 1Password, which is a nice feature. So you can, go to a website, say, fill in my name and password, doom, and then it copies your current token to your clipboard. You would enter. Now you're the thing where you enter your code. You hit paste, and that goes on. Journal and backup is when I was working on this talk for work. I originally gave this talk in a really abbreviated form at our local hackers group, Nova Hackers, back in May, and then I tweaked it to give as a lunch and learn at work. And as I was, enhancing the slides and going through and making sure I didn't miss anything or screw anything up, I found some keys that I didn't recognize, some data structures that wasn't there before. I don't know what the hell this is. And I dug into it for a while, and eventually reached out to Agile Bits and their support forum. They said, "Oh, nice hunting. Glad you found that." It's a new feature that they're building where it will encrypt your passwords as you change them with a new key. It's also based on your password. That's 500,000 rounds of PDKDF2. But it encrypts them as you change them and stores them somewhere in the database. And then at some point during the day when you're not doing much, it finds everything that's changed and writes them out to a file. And the idea being there that they will get a consistent journal of things that have changed. So you've always got a backup, but it's not doing it in such a way that it takes a long time out of your day. So if you're sitting there trying to get to a password and it's in the middle of doing this process, it's going to be super slow. So they kind of split the process up into encrypting and dumping this way so that it doesn't impact the user. But that feature is not live yet. Even what I saw in 1Password was only halfway there. So this could also change a million ways from Sunday before it finally gets released. But it's kind of fun that I found that. There's clients on phones. I haven't looked at those. There's clients in the browser. I touched on that. There's an official command line client, which is a pain in the neck, but it's incredibly powerful. There's browser extensions. There's security issues related to browser extensions, because then when, how does the browser talk back to the 1Password thing? And they've talked a lot about how that works. There's the ability to send passwords to other people through SMS, which is just obfuscated with a fixed key. I haven't really dug into how that works. It's good if it's an emergency, but then after the emergency passes, you should probably change your password. And then Touch ID is great. On the Macs, the newer MacBooks, and I guess now the iMac Pro have Touch ID sensors. And it used to be that it would store basically the login data that was encrypted with the master unlock key. It used to store that in your keychain, and there was, when you authenticated to the Mac by touching the Touch ID, it would then provide the contents of that keychain entry back to the application. The application would then look in your preferences file, pull out a key that's hidden in your preferences file, decrypt it, and now it's got access to it. That's reasonably good security. You need access to the box, you need access to the preferences file, you need access to the keychain. And theoretically, you couldn't get to the keychain unless you're the 1Password app. But, and I haven't dug, really nailed this down, but it seems like if the keychain is synced over iCloud Keychain, then you can retrieve that with some work on other Macs that are also subscribed to that iCloud Keychain. So it's actually possible to pull the secret out of there and then pull the secret out of the preferences file in the first box, and you can decrypt it. With the newest versions, with 1Password 7, it's actually changed that. The secrets are now, the key is in the secure enclave on the box, the secret is in the preferences file. When you unlock it, it's decrypted by the box. You'll never have access to the key. It can only be done on the box. It's significantly safer. So if you've got a Touch ID Mac, using 1Password, absolutely upgrade to 7. It's a lot better for that. And that's it. I'm really grateful to Agile Bits for being so transparent about how their system works, and especially for answering all of my questions. And I kept throwing really ridiculous, obscure technical questions at them, and they were all very good about answering them. And then, of course, Expel has let me kind of turn a simple question we had in a table talk into a long talk and a whole really long set of blog posts. And if you want to, there on my blog, I've got this. I just published it this morning. It's 5 different sections plus a beginning and an end, and all kinds of data, ridiculous amounts of technical detail. I also have on the GitHub repository, I put some simple example scripts that you can use to decrypt the data. So basically you can say, I want to decrypt the muck. Okay, what's the salt? And you go to the database, you find, okay, here's the salt. What's the IV? Okay, get that. What's the thing? And so you copy all the different things in, and it spits out the answer. So you can use that to really just walk through a 1Password database, you know, block by block, and decrypt individual things. So you start out by decrypting the muck, which then you decrypt the key set, which then you decrypt the first private key, which then you can decrypt the vault, which then you can decrypt an item. So you can prove to yourself that this is all actually working the way that you think. And then because doing this on your own password data is probably not a bad idea, I was actually able to set up staging accounts, and I did those for a while. Then as I was putting together this talk, I said, you know, I really need just test data. So I've actually got a whole script that generates all the different data structures for you. You can use that to create some test data and prove to yourself that whatever tools you're building work, and then when you're confident that works, then you can try it on real data. But even that, you know, it's passwords, be careful. So that's it. Any questions? It's a lot of data, I know. Yes.
Does 1Password support YubiKey as a second factor?
Does 1Password support YubiKey as a second factor? And they don't yet, and I know there's been discussion about it on the forums, and they have answers, good and bad, and I'm not really sure what the planning is. I think there's an argument to be made that that things like that might be too, and this is me speaking, that things like that might be a little bit too tied to specific vendor, specific niche technology. It's a great idea. I mean, and they're already doing that by supporting Touch ID on the Macs, but that's a lot less niche than a YubiKey. But no, they don't support it at this point.
There's a push right now for NIST to actually standardize that for using YubiKeys or the equivalent. So I just want to mention that if you weren't aware of it.
Okay, a push from NIST to standardize the use of the
use of YubiKeys,
yeah, use of YubiKeys and stuff.
That standard,
yeah,
for use with lots of other technologies.
Yeah, YubiKeys are neat. I did some digging a while ago for another talk into how different web authentication systems work, and I love the whole U2F framework and interaction with YubiKey, but it was not very well supported in the browsers. I don't think Safari still supports it, or I think Safari still does not support it. There's a lot of negatives in that sentence. But it's a great idea, and if we can start getting more pushback on that to get that more widely supported, that'd be great. Any other questions? Yes.
So with all this great technology, is there anything that they're doing around the simple reset password using the email stuff? Because you know that's kind of secret since the entire. Are they forcing MFA or anything that is out of the ordinary? When someone is hacking an email, eventually they can kind of start everything from scratch.
Yeah. So the question seems like a couple of parts. Part of it is addressing the question of password resets, just a pain in the neck. And I don't know the details, but I know that there's some efforts underway, not by Agile, but just in general in the community, that there are some efforts underway to standardize, possibly even at the API level, a way to change your password. Mm-hmm. And the idea there being that eventually password managers could say, hey, your password has been breached, type in here, and boom, 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 you change it, and 1Password will reach out to the service and change it for you. I know that that's being worked in general, but I don't know if any of that has made any progress. And then enforcing MFA, you know, all that's coming down to, obviously, to the individual services. But again, with that Watchtower feature where it's saying, you know, this site was breached more recently than your password was last changed, or this site has been weak. They actually have a feature there where they say, hey, this service supports MFA and you don't have it enabled. You might want to consider that. So they kind of do have features in there that can help prod you that way, but there's nothing that you can do to enforce that. That's going to be at the service level. Any other questions? All right, thank you very much for coming.
Thank you.